with that. Some of them were really, really good, some of them weren't so great. Anybody have a question about the 2.4 work that I No? No questions? All right, then we have one more problem in our main notes to wrap up. So let's take a look in our notes. Here on the back of page 12. We did not yet do example 5. So with the back of our notes, do example 5. So 50 deer were introduced to a large wooded area. Population can be modeled by the exponential function. T is years, and D of T is the population of deer. The population of deer increases by 13% each year. So, given that information, you should be able to write your equation. Anybody want to take a stab at it? Charlie?
Is 50 like the 0? Is that what it is?
50 is the initial value, and this is your initial value right here. So yes, you're right, Charlie, we're gonna start with 50, and then what?
Then since the population of deer increases by 13% each year, it'll write 1.13.
Yeah, so we write 1.13 to the T, where T is the number of years. Is that okay with everybody? Didn't that make sense? According to the model, what is the population of deer in the large wooded area after 6 years? Well, what are we going to do? Plug in 6. That will be a calculated problem. So 50. And let's answer reasonably since we're talking about deer. Shall we just say 104? Would that be okay with everyone? Would someone nod at me or shake your head just so I know that? Okay. Thank you, thank you. Find the time T when the population of deer in the wooded area is expected to reach 5,000. Now, what's that going to look like? We're going to put 5,000 in, but not up here. We're going to put it right here, aren't we? So 5,000 equals 50 times 1.13 to the T. So we're going to solve this algebraically first, and then we're going to solve it graphically. If we're going to solve this without a sketch, algebraically, just algebra stuff, what would be the first step? Divide by 50. You always want to divide by 50. Get rid of that. And this one works out nice. So we have 100 equals 1.13 to the T. Now we need a logarithm. All right, everybody? A logarithm of both sides. Now I am going to take the log of both sides. Could I take ln both sides? Yes. They are the same. Well, I can't say they're exactly the same thing, but the types of logarithms, they work the same way. Just whichever button you're using on your calculator. So we have a log of 100 equals T log 1.13. When you take the log to a power. The power can be pulled out front and it turns into a coefficient, which is the beauty of logarithms, because now all I have is a division problem. So t is the log of 100, which by the way is something special, over log 1.13. So let's type that in, see what we get, and we're going to graph it and verify that we get exactly the same answer. Did you get 37.680 years? Does that sound okay? All right. Now graph this on your calculator. If you want, you can divide by that 50, so your numbers aren't so big, it really doesn't matter. Just let me do that. On that? Everybody get the same thing both times? Alright, last question. Find an equivalent expression. Here's what we came up with right here. Find an equivalent expression where t is measured in months instead of years. The initial value isn't changing, right? I mean, we have 50 deer, no matter how we're measuring time, we have 50 deer to start. The annual growth rate isn't changing, it's 13% per year. So this is staying the same. That means the only thing that can be altered is the exponent. So this was in years. We're going to turn that into months. What do you think? T over 12, she says. Celeste, explain your logic.
Because there's 12 months in a year, so you divide like 9 years to get like 12.
So every month is a 12th of a year. So she says, let's look at what she says. She says, okay, what if we waited 12 months? What if we let t be 12? Wouldn't that be the same as just 50 times 1.13 to the first power? I think she's right. Now, that is the same as this. Would you agree with that? So So we can actually find, this is our annual growth constant, 13% per year. We can actually find it per month by raising 1.13 to 1/12th power. We're taking the 12th root of it. So the monthly equation would look like this. It has a whole new constant. Notice we didn't divide this by 12. We raised it to the 1/12. All good? All right, let's go to the back of page 13. Check your understanding. Talk it over with your partner. Let's see if we can figure out what's going on back here. Up at the top of the paper, and where it says quick notes, I put a couple of formulas there for you. Compound interest, we did that last year. Does that formula look kind of familiar to you? You may not have used P sub naught, that just means the initial value that you're keying your principal that you invested. All right, so see what you can come up with those three problems. And we'll get them on the board and talk about it.
At this time, please do not leave the building. At this time, stay in your classrooms and do not leave the building. We will make another announcement shortly.
And we can keep working. Maybe it's a forward one. I don't think we're going to go out, but we just keep working and we'll see what happens.
Again, at this time, nobody should be leaving the building. Everyone should be in their classrooms. Please do not leave the building.
Okay. Keep working, let's get this done.
We apologize for the interruption. There's a technician working on some controls, and that was an accident that went off. We should be good to go. You can resume class. Nobody should leave the building.
Okay. should have number 1 done. How did you answer part A? Increasing, and how did you justify that? It's exponential growth, and remember, exponentials are either always increasing or always decreasing. There's no variation in them. So when you have a B value or an R value that's bigger than 1, you are growing all the time, no matter what years they picked, you're growing. What does the 30.92 represent? Charlie?
The initial, value of the
Well, yeah, so how many, there were 30.92 million households with this kind of TV in the year 2000? That was the number of TVs in the year 2000? And then the 1.012 represents 1.2% growth every year. 1.2%, everybody okay with that? And then did you get a number for C? Did you type it in and get a number? 36.978 million. Million, make sure you put a million on that. Good. I'm gonna move out of the way. For number 2, you need to see a setup for weekly, monthly, and continuously. Anybody come up with those? Using the formulas at the top. Weekly will be your compounded compounded interest formula, compounded finitely. So we want to know how much we're going to end up with, and the notation used here is function notation, that's fine. And T will be what? It is 25 years. We're going to find a value after 25 years, and our formula is going to be 25,000. The interest rate is 0.0875. And if we are compounding weekly, then N is 52. The N in the formula is 52. Raised to the 52 times 25 power. Monthly will be exactly the same thing, only N, it would be monthly, N would be 12. And then continuously is a whole different formula. So with the 25,000, then E to the 0.0875 times 25. Alright, so take a look at those setups. Ask a question if we have it. We just kind of snuck those formulas in. We didn't really talk about them. weekly one, I got 222,413.32. I don't know if that's right or not, I don't know if I typed it in right. Monthly, I got 221,061.10. And for continuously, I got 222,822.57. All right, take a look at those, type them in, see if you agree. Anybody have a question about the formula or how I got those numbers? Or even if those numbers are right. They look okay? Do they make sense? Because the more times you compound, the more money you're gonna make, right? And so monthly is gonna be the least in this scenario. And of course, continuously will be the most. All good? All right. Number 3. What equation would give the number of bacteria after T hours? Did you get this far yet? What'd you say over there, Lily?
1800 e to the 0.0812.
Perfect. So y equals, or p of t equals 1800 e to the 0.081 t. Perfect, perfect. And then to find the number of the bacteria in 6 hours, we would just plug in 6. Right? I got 2926, 2,926. All right, one more page and we're moving on. Back of the next page, back page 14. Try your luck at these. I would totally love to have somebody put something up here. I don't care if it's 1 or 2 or A or B. But I'd love to have somebody besides me put something up on the board. for A?
70.3125 grams.
Okay, tell me how you got back.
I did 45 times 1.25 squares.
Okay, so let's look at this for a second and see what's going on. So it is known to decay by 25% every 5 years. So this would be the beginning, this would be after 5, and then after 10 days, after 10, we know it's 45. So to get from term to term here, this is decaying by 25%. So that means these numbers are getting progressively smaller. And to get the next one, if I wanted to know, okay, after 15 days, or hours, whatever it is, I would take 45 and multiply it by what? 0.75. So to go forward in time, I'm gonna multiply by 0.75. How am I gonna go backward in time then?
1.25.
Divide by 0.75. So if I take 45 divided by 0.75, this was 60. Because if you take 60 times 0.75, you'll get 45. And you go back one more. I think there were 80 to start with. Does that seem okay? And then if I want to write all this in a formula, what's 80? 80 is my initial value. So 80 times 0.75, because that's what we multiplied by to get a 25% decay. You gotta be careful though. What's wrong with that? Charlie?
You add a 1/5 to that T.
Yeah,
divided by five.
gotta make that T so it is not in 5-year increments. This T is in 5-year increments. So we're gonna divide that by 5 or make it 1/5 T, and that would be your equation. Remember, this 0.75 is every 5 years. So there's a lot of years in between there. Good job. And then did anybody look at C? Charlie?
I know something that's actually pretty cool. When you like multiply all that out, you get 0.944, which actually if you multiply or do 0.75 to the 1/5, you get that same base.
Huh.
Yeah.
So, wait a second. You actually calculated e of 7 over e of 6.
Yes.
Okay, this was e. All right, so you put 7 in here and got a number, you put 6 in here and got a number, and calculated that and got what, 0.944. Okay. Then you came over here and said, well, that 0.75 is my 5-year number. I could rewrite this like this. This is exactly the same thing. And this would be my
1 year.
every year number. And oh my gosh, when you type that in, that came out to be 0.944, you say? Now, are we shocked by this? No, because this is the ratio of 2 consecutive years, right? If you look at it, this will be 80 times 0.75 to the 7/5, 80 times 0.75 to the 6/5. And I know you typed it in, I got numbers, and that's great. The 80s are gonna cancel. These are the same base, so I can get a simplified version by simply subtracting the exponents. There it is. Yeah, exactly. Beautiful, Charlie. The rest of you follow all that? Okay, did anybody make it to number 2? Not yet? All right, let's work through it together then. See what's going on. We need an equation like this. These are like the ones we did the other day, only they tell us what our C is. We know our C is 3, and that's because that's what the refrigerator's set at. So if you think about this temperature, here's the temperature coming down, cooling off. But because the refrigerator is set at 3 degrees, we aren't going to be able to go lower than 3 degrees, right? That's where our asymptote is. That's what that is. That's your asymptote. Okay. At time 0, it's 180 degrees. For 10 minutes, it's 150 degrees. Okay. You can do this. If we put a 180 in for our Y and a 0 in for our X, that's the initial. Can you solve that for anything? Yeah, what does that say? A equals what? $177? So now we know A is 177. So what should we do now? Plug in the other point? So 150 equals 177 b to the 10th plus 3. I put in this point. So the x is, or t is 10, and c of t is 150. So 147 equals 177 b to the 10. I'm going to solve that, so what am I going to do? Divide. So 147 over 177 equals b to the 10th. So now I will 10th root it, or raise it to the 1/10th power, whatever's easiest for you. And I got b to be 0.9816. I'm gonna carry an extra place there. So my equation is 177.9816 to the t plus 3. Does that number make sense? I mean, would you expect it to be less than 1? Yeah, because the temperature is going down, cooling off. And then what would the temperature be after 45 minutes? We'll just plug in 45. And that would be that. I got 79.741 when I did that. Any question about that? All right, that homework's gonna be due on Wednesday, and now we're gonna take a quick to look at least the beginning of 2.6. Throughout this course, we will have, and already have had, many opportunities to work with and create models based on a given data set. Three particularly important examples of this are linear, quadratic, and exponential. Because these three types of models occur frequently in the real world, there's a heightened focus on them in this course. On the AP exam, students will be expected to determine which model is most appropriate given a set of data. There are a few strategies and methods that we can use to determine whether a linear, quadratic, or exponential model is most appropriate. Okay, so we could be given a picture, we could be given a data table, and we have to be able to decide. And obviously, if you have a picture, it's pretty easy, right? And you know what lines look like, you know what parabolas look like, you know what exponentials look like. So if you've got a picture, it's okay. How do we tell from a data table? We've already practiced this. How do we tell? If the data's linear, then the rate of change will be constant or close. Remember, we're taking real life data, so it isn't ever going to be exactly linear, but your rates of change should not be jumping around from negative 2.7 to positive 6.3. That would not be linear, right? All right, how about quadratic? So that would be the actual average rate of change. So if it hits quadratic, some of the slopes, some of the average rate of changes will be positive and some will be negative, right? Would you agree with that? And they should be changing at approximately the same rate. Remember when you do your little chart? And they're going from the rate of change is going from 2 to 5 to 8 to 11. That's a linear relationship. They're changing by approximately the same amount. And an exponential, you should see something that is proportional or some kind of multiplication going on. All right, example 1. Here we go. Take a minute, you and your partner. See if you can figure out what fits these tables, what fits this data. chatter, chatter, I hope it's about math. I hope you're coming up with good reasons for whatever it is, however you're answering.
Like rap.
All right, we're almost out of time. Has anybody come up with a good explanation for any of them? Oh, I'm gonna have to just call on someone. Alberto, what do you think about A?
I think it's linear.
You think it's linear?
Yeah.
What was your reasoning?
Cause they're all going down like a boundary.
And when, yeah, and when you plotted them, they kind of all fell in a line, didn't they? Yeah. So would you all agree with that one? Notice that the rates of change are not exactly -3, but like he said, they're close to that. They're kind of all approximately that. Okay, who came up with something for B? Quinn?
Yeah, I was gonna say quadratic, because the values grow and then they drop.
And even the points they gave us have some kind of symmetry, don't they? I mean, they're lined up really closely together, so I would agree that that is quadratic. How about C? What do you think about C, Parker?
Exponential.
Exponential? Does that look like decay to you? And when you examine the rates of change, well, they're definitely, I mean, slopes are all negative there, but they don't appear to follow the same kind of pattern that they do in problem B. All right, and what do you think about D?
Exponential.
I think that one's exponential too. Only that's a growth, right? That's a growth. All right, tomorrow we'll continue this conversation. We're going to talk about residuals again. So try to refresh your memory on how to find the residual plot, because we're going to do it next 2.5